Hello everyone. Our team include Isaac, Antonio, Lynn, and Miguel, and we'll be talking about our mechanical system designs project, which is a curtain roller. Let's begin by discussing the motivation behind our project. We want to develop a tool that will benefit two main groups. First are those with disabilities who may have trouble manually adjusting their window curtains, and second are those who respect their privacy and would rather not have to deal with manually operating their curtains. We improve accessibility, efficiency, and comfort by automating this daily routine process. For our goal, we want to use a light sensor to activate the motors so that it can automatically raise the curtain to let in natural light when there is sunlight outside, and lower the curtain to provide privacy after sunset or within any dark area. The axis of the curtain pipe is rotated by a Grashof linkage system. Moving on to how the mechanism of our automatic window curtain system works. There will be a long pipe which forms the central axis for the curtain. The two ends of this pipe are securely connected to one side of the hubs, providing stability for rotation. The links are paired and connected using ball bearings and pins, allowing smooth movement. One end of these links is fixed to the wall, while the other is attached to the opposite side of the hubs, creating a stable yet flexible structure. For the automation part of the device, a light sensor is used to monitor the surrounding brightness. The sensor provides signal to turn on the motors when it notices variations in light intensity. Finally, the hubs will rotate along with the links as the motors are activated. This rotational motion is transferred to the pipe, enabling the curtain to roll up when sunlight is detected or roll down when it gets dark. Since the rotation is based on the Grashof linkage system, it ensures a smooth operation and user convenience, making it a practical solution for everyday use.
This video shows a simulation of how our project will move. It will retract the curtain in one direction, or unravel it in the other direction. This will be done by attaching the outer links to motors, which will be activated by a light sensor. The goal is for the assembly to rotate the curtain either direction at a speed of 60 revolutions per minute.
When it comes to the quality function deployment of the curtain roller, it is best to utilize a household quality tool in order to set and define parameters as a team for our mechanism in regards to our customer requirements. This tool is then a product planning matrix that is built to show our customer requirements and how they relate directly to the ways and methods we would ensure those requirements are achieved. This will ultimately lead to customer satisfaction and loyalty towards the curtain roller due to its reliability and efficiency. Efficiency will be obtained by understanding the customer to a better degree and breaking down the detailed engineering specifications needed to meet their requirements. These specifications are meant to be measurable and can be developed from design experiments and analysis. This tool also compares these same specifications with other companies with a similar product in the Now section in order to help justify our own ratings in the House of Quality for the How section. The Now section is a rating between 1 through 5, where 1 is a bad rating and 5 is a good rating. The How section is a rating of either 1, 3, or 9, where 1 is a bad rating, 3 is a decent rating, and 9 is a good rating. This ultimately all comes together to show how our product aligns with the requirements and specifications needed for a curtain roller, along with comparing these points with possible competitors to show the customer why they should pick us over them.
Moving on to the kinematics of the curtain roller, the main focus was ensuring the rolling motion of the mechanism. This includes both the clockwise and counterclockwise direction for rolling up the curtain as well as unraveling it. Once this rolling motion was considered, the next step was focusing on ensuring that the mechanism had a proper load distribution once it was fixed in place by the support of a wall. This proper load distribution was then implemented by splitting the components of the mechanism into A and B categories for the sake of equally distributing the force being applied along the pipe of the curtain roller. Since the team decided to manufacture the roller curtain at a PVC rigid custom, it was decided that links attached to a hub would be the best method of providing the drive needed to make the roller curtain function. This material being utilized meant it would be cheap and easy for the team to manufacture due to the availability of the material and capability of this material being 3D printed. In the assembly of the curtain, then lies link 2, link 3, the hub, the ball bearing and pin that joins them together, and lastly the pipe to bring their overall A and B components together. All these components were given basic dimensions such as diameter, thickness, and length in metric units. These metric specifications and dimensions were then set and justified by the team in respect to our requirements set in the House of Quality. Each component on the image to the right of the slide was then given dimensions in order to create their counterparts, and then fully assemble the mechanism to provide our team and the customer a visual aid to help understand the intended kinematics for the roller curtain, and also provide insight on what makes this design unique from our competitors.
In this slide, we showed the logic behind the bearing design. Some of the assumptions we came up with were a 20 Newton axial force and a 120 Newton radial force. We also included a 10 millimeter bore, assuming light impact, 99% reliability, and a speed of 60 revolutions per minute. And because we assumed that the curtain roller would be operating at room temperature, it was obviously going to be much less than 150 degrees Celsius. We also assumed that we were working with inner ring rotation. So, applying all of these assumptions and boundaries into the tables, we calculated the total load life of the system. This resulted in about 2 times 10 to the 6 hours. This is a pretty high figure, but some of the reasons for that include an overabundance of caution, as well as a somewhat lack of resources for our particular design. If we were to go through with physically manufacturing this, we would go with the groove much smaller than what the chart displayed information for, or perhaps not even include one at all.
With stress analysis, we did several things here. The first thing was we assigned the material, which in this case, we did a PCV that was a custom made. That way we included the yield strength to this material assignment, as well as the thermal expansion coefficient. Then after that, as we move on to the mesh generation, you can see not just that we created a mesh to allow us to have the most accurate simulation possible with several thousand nodes and elements involved. We also have in there the direction of the forces. As you can see, we applied a 20 Newton force load to the PCV shaft in the center. And yeah, as we move on to the next slide, stress analysis, you can see the factor of safety and stress analysis with the von Mises plot. Specifically with the von Mises plot, this is once we assigned our forces as well as our boundary conditions, which were our fixtures. We conducted the stress analysis, and from there we got this von Mises plot. And as you can see from that plot, our stress did not exceed the maximum yield strength. In fact, we were well below it. The maximum stress that we got was 5.00. It was 5.062 times 10 to the 5th. And then the yield strength, the allowable yield strength, was 5.00 times 10 to the 7. So, with this being said, our stress was well below the maximum. And then from the factor of safety, we got from the simulation as well, which was a 99. And this is an extremely high value, which we know should have been less. However, we did see as well in the plot that, or in the factor of safety plot, that it was so minimal that it was almost negligible.
Here are some of the references we use for research during the duration of this project. And that concludes our presentation. Thank you very much for listening.